Bismillahirrahmanirrahim. Now, in order to calculate the stresses at the corner of a pavement, a rigid pavement, we have to apply this relation that has been derived by Westergaard in 1926. And according to that, the formula for calculation of stresses at the corner is 3 times P is the load, H upon H square, H is the height, A is the contact radius, this small l is radius of relative stiffness. And if one is interested in knowing the deflection, it has to use P, and then he has to use K, he or she. This is a modulus of subgrade reaction, K, and this is the stiffness, and just apply this formula. This is for circular road. So let's solve an example. And this is example 4.2 in the book, in which shows a concrete slab subjected to a corner loading, given that K is equal to 100 PCI, H is 10 inches, A is 6 inches, and P is 10,000 pounds. We have to determine the maximum stress and deflection due to corner load by using equation 4.13 to 4.16. Or in other words, we have to use this Westergaard relations. So again, we make this table and we'll try to list down all the parameters that needs to be calculated in order to calculate the stress, our objective, or in this case, stress at the corner. As we know previously, that in order to calculate radius of relative stiffness, we need to know the modulus of subgrade reaction K. The Poisson ratio 0.15 is assumed that it is taken for the concrete. Depth of the slab is 10 inches and E is 4 into 10 power 6. Remember, this can vary between 3 to 7 millions. So when we apply in this formula, remember this is the fourth power rule, or in the word, if this whatever is the value of these, we have to take 1/4 of that. And that's why we have got relative stiffness as the unit is inches, so 42.97. As shown in the previous slide, if you want to know the stress at the corner, we need to know P, the contact radius 6, A, the stiffness and the slab thickness, and we found that it is 187 psi. Just it's nothing, simple input of the values. For deflection, we need P, the K values, and the stiffness value, and there we find the deflection of the corner is 0.05 of an inch. We now go to another problem. This is the stress due to loading. Again, we have different places, different configuration where we want to find the stress. The first one is where we think that the wheel is the center of the slab. And for that, we have the relations. Sigma I is we need to calculate the stress at the inner portion or the stress at this point. Here, mu is nothing but the same Poisson ratio. Uh, this this is natural log of radius of relative stiffness and B, and this is a constant. Now, in order to calculate B, we have been given this formula. B is equal to 1.6 times A square plus H square, and we have to take the square of it, this. And from these value, we have to subtract 0.675 times H. If A is less than 1.724 H, otherwise, you don't need any of these things, this formula, to assume B is equal to A. So you are only going to use this formula when you find A less than 1.724 H. So if you have been given this problem, first calculate A and compare first compare A with 1.724 H. For knowing the deflection, you have been given this equation. This K, don't we get confused. It is the modulus of subgrade reaction. The other all values are explained as well. This can be another formula where we can calculate sigma I and delta I. So again, we go the same way as we were going before. We'll make the table, the 4-column table. First, we'll calculate radius of stiffness. And then, as I was referring, that you have H and you have to check A, if the value of A is 1.724 times H. So since A is 17.24, therefore we have to find is greater than what the value of A that was given to us was what? I think it was more than it was 20 inch, I guess. So that's why A is 17.24 and A is greater than 1.724 H. Therefore, we have to find B. For finding B, we know A, we know H, and we found B is equal to 5.80. It's just we are substituting the values and getting the required parameter. The stress, we know P, we know B, we know stiffness. Or we have calculated stiffness. We know H, so that's why the interior of the stress is 143.7 psi. The deflection, we use this equation, and that comes out to be 0.00670. Now we will discuss about stress due to edge loading. The fact that both stresses and deflection are greater under semicircular load than those under a circular load is reasonable. The centroid of semicircle is closer to the pavement end that is of the circle. So if you want to calculate stress at edge of the slab, then this is the table and this is the solution for example 4.4. We have to find radius of stiffness. We know the formula, we found 42.9. Stress due to circular area, we found as 279.4 psi. And stress on the semicircular area is 330 psi. So we can say that the fact that both stress and deflection are greater under semicircular area than those under a circular area is reasonable, because the centroid of semicircular is closer to the pavement edge then that of a circle. So whenever there is a loading in which the half of the wheel is located at the edge of the slab, it will going to create more damage. So though we have to be very careful and in knowing these type of stresses, because this is where you have the problem of a corner cracking. And normally, a vehicle is vehicle when you drive a vehicle, it is on the center of the road. This happens only when there is a undue traffic congestion. So if there is undue traffic congestion, then there are chances that we may come at the edge of the pavement. And that is where uh, we need to be careful. And that's why when we draw or when we design our pavement geometrically, we must have enough lanes to accommodate traffic. Otherwise, even the concrete pavement will be breaking. So I think I stop here for example 4.4 till, and I'll have another session of these problems in the next class.